Hey, hello, hi everyone. And today we will be discussing another same. Uh, we'll be discussing trees and graphs chapter, the remaining few problems from the last session. And this is a CTCI SD skills session. Okay, so let me actually share my OneNote first. Okay. Well, okay. So what I'm proposing, today we'll discuss trees and graphs, and there are three still problems which were remaining from the last session, which I thought should be covered, and some of them are interesting, and I think one or two are, they we might have worked somewhere in a elite code or so, but I thought let us go through the same, the way it's in the CTC. Okay.
Yeah.
Yeah. So the first problem is it is about the BST, the binary search traversal sequences. Okay, binary search tree sequences. So he says that if there is a binary search tree, if we are given a binary search tree, and the binary search tree is actually created by traversing through an array, right, from a left to right, and inserting in it each element. So when we are given a binary search tree with distinct elements, okay, they are not repeated, then print all possible arrays that could have led to this tree. So the example here, it says it 2 is a root node, and then we have a left node as 1 and a right node as 3. And so if you look at the output, in this tree, if it's converted into an array, or maybe if we are given such an array, and if we were asked to create a binary search tree, we'll always create uh, the same binary tree, right?
Yeah.
Yeah. So he's saying that whenever we are given a binary search tree, we should create all the sequences whatever are possible. Okay. So if you look at this diagram carefully, so your 2 is the root node, and for both the outputs, 2 will always be at the beginning, correct? So when your root node is at the beginning, so irrespective of whatever your nodes are after that, you know, you can still form a binary search tree. That is what it says, correct? So
Yeah.
a single binary search tree, if we were supposed to create sequences, we can create many sequences. So I thought this problem was interesting because it's not given anywhere. Have not seen that in lead code geeks for geeks also, and it might not be that hmm, what you say popular, or maybe it's not so much liked by people also, but it's not that. But if you, the interesting part of it is like you can create many sequences. Okay, when I was just working on this problem, then I saw. So now in this case, if you look for this second solution here, so where we have this 50 as a root, okay, and then we have 20, 60, okay, this is such a big one. And if we actually run through, okay, the solution what I already have implemented, you can see that it creates about approximately, I think 2000 such combinations. So they are huge. Okay. So what it says is every time, for each and every time, like in this solution also, if 50 is at the beginning, okay, then you can recursively think how to construct it, right? So one is
Mm.
you can say that this is your subtree of 20. Okay. So this is a 20 subtree, and this is a 60 subtree, right? So when you create that, so whenever you actually, what we can do is you can take the subtree 20 and subtree of 60, and then weave them together, in the sense intermingle them together, and append it to our root node, right? So if you look at this above example, where you say where you given like 2 1 3 and 2 3 1. So right, what they have done is actually they have just taken this 1 and 3 and they have intermingled. Here you don't have much scope, so therefore you just, if you reverse them, that is the only two combinations you get, and you just append it to your root node, right? So then you can form all these combinations. So same thing if you keep doing with this 20 subtree and 60 subtree, you can imagine that how many combinations you have, right? So in the next step, now first we have something like 50, okay, appended by your 60 subtree, right? But when you construct the 60 subtree, every time your in that subtree, your 60 should always be at the beginning, okay, and then it will follow the same principle again. So it will also have, now in this case in the 60 we have only one right subtree, right, 70, okay. So
Mm.
there is not much of scope in it. But if you look at the 20 here, you have a left subtree which is 10, and you have a right subtree which is 25. So in that case, your 20 will always be ahead of 10 and 25. Okay, and then you can intermingle them anyway. So you can have 20, then you can have 10 first, or 25 first, either of it. Okay, so you got the point, right? You can make these sequences many of them. You can just create if the nodes are more. Okay, and so the way how it is done. Okay, so there is an example what is given. The main crux of the whole algorithm is weaving. Okay, so now for example what weaving means, like if you were given a two arrays, array 1 and array 2. Okay, so array 1 and array 2, if both of them have only two elements here, 1 and 2 and 3 and 4. So if we weave them, so you can see like it can form so many combinations. They have not shown all the combinations, but at least few of them. So if you see, they start with 1 first for the first row, okay, and then then this 2 is separated. Okay, so the first 1 is separated from 2, okay, in this case, and then 1 is always at the front, okay, but then you take out 2, okay, and then 3 and 4. So 3 and 4 remain same. So you just weave this 2 along with 3 4. So first 2 is before 3 4, then 2 is between 3 4, and 2 is after 3 4, right? So that's very simple to follow. And then in the next one, what they have done is, because you have to maintain this sequence order, okay, every time. So that is very important when you have to weave them, right? So for 3 and 4 also, if you look carefully about the sequence of 1 and 2 in the first one also, 1 and 2 will always be, 1 will always come before 2. Obviously 1 we have taken care of first, okay, we are actually uh, keeping 1 aside, right? And then we are just taking 2 and 3 4 and forming all these combinations, right? So that is very easy to follow, that 1 will always be ahead of 2. Okay, but if you look at 3 and 4 also, in this the order is not actually changing. 3 4 is here, so in this case also, if you want to form a subsequence of 3 and 4 in the second one, you will still get that, right? So that is the way it has to be done. So this is what the weaving is. So the weaving actually, the implementation is like, if you, the same one, the example is the function what he is showing here is, the prefix is nothing but you actually assemble your inputs. Okay, so in the first prefix, if you have a weave such function, so the way actually is shown in the book, it says like the first will be your first array, second will be your second array, this array, and then prefix is something which is actually empty initially. Then you first, what you do is you pick up one from this first one and then push into the prefix. Okay, so then you again recurse, and when you are recursing for the first array, so then you remove 2, which is from the beginning of now your array 1, and then push it back to your prefix, right? So your base case of the this recursion will be either of your prefix, sorry, either your for first array or second array, either of them are empty, right? Then you just combine the prefix with whatever remaining arrays are, right? So in this case, what we do is we take this prefix 1 to here, okay, and then we just append whatever is in the second array. Okay, so now we form one combination. Okay, then we come for the second one when we are actually recursing and when we are going back, right? When you have completed one thing, one recursion, we complete the base case, then we start backtracking, right? So in that case, what is doing here is, so we were here in this case, right? So if you look at this case, right? So this, after two, so he just going to the second list now. and taking the first element of the second and then pushing it to the back of the prefix, right? And then the same thing you do, because it's again uh, sort of a recursion of two recursive functions. Okay, so the first will be recursing the first one and the second will be recursing the second one. So if you look at once we are done with the first function, you come backtrack and then you start with the second one, you push the 3. Okay, and then when you push the 3 in the second one, what you do, because you'll again hit on the first function. I'll show you how the implementation is, but I'm trying to explain it here first. And then you just take the 2 and then again that will actually go and append to this the prefix. And now if you see our first array is empty, so now you can append, take prefix 132 here and then append whatever is remaining the second array, so 1324. So this is the function what they have used, and it's very interesting because it has two recursive functions in a single function. Okay, so that way actually you can form a recursive function which will still maintain the order, okay, but it will weave in different combinations. Okay, so this is the whole crux of the implementation. So I will just show you this. Okay,
It's a
well,
template. I mean, it's a bit clumsy to get it right.
right. Therefore I am trying to explain it, because it took some time for me to understand. But once you actually get a feel of it, and it's still not so easy to get, I'm very sure. But if you get that, but the benefits are very great. Okay, before even I show you the walk through all the code, I'll just say now what I'm done is I've taken only a few of these array. Okay, one is root node is 50. Then I've just taken, this is my left subtree and this is my 60 is my right. On my right I am having only one node, and on the left I am having 20, and then I'm having 10 and 25. With this only 5 of these, if I run this and see the number of combinations what I get 8. Okay, so if even if I just add one more, the 70, which is also to the right side, and if I just run it, and if you look at this, the combination, it gets to 20, right? So but if I take the whole tree, okay, and then just run the whole thing, uh, so if I run all of these, and if you look at the whole combinations, it's huge. It is still 19, 18 something. So you get about 2000 such combinations, right? So
Yeah.
they are very big in number. And also if someone thinks, this is whether it is really forming a node or not, but whether it is really forming a BST. Okay, so I have another function. What I do is, the way I'm printing, whenever I'm printing each and every sequence of this weaved function, so I also pass through a BST. So what this BST does is it takes the input array, actually this whatever we have formed from this, and then it creates a binary search tree. Okay, a simple binary search tree. So if you look at this one, now we have only 1 2 3 4 5 our earlier one. So everywhere you will see a BST form. So this is only the 8 for things what we have done, right? So we have 8 combinations now. So if you see this sequence, whatever we have, and if you pass it to the BST and try to form it, so this is in order BST, and therefore you see it's always sorted, right? It's the same thing. This is just to prove, that whatever sequence we form here actually can generate a BST. Okay. So if you look at,
Yeah.
these are the 58 combinations, and if I just comment this, because it clutters a lot, right? And then if you just carefully observe, so you see this 50, which is our root, always will be at the start. Then you have a 20 subtree, right? And then we had a 60 subtree, correct? So you see the 20 subtree and 60 subtree, they can be at any place, no problem, because sometimes 60 is first, 20 is first. But whenever 20 is there, its subtrees, which are 20, 10 and 25, they will always follow it. They won't be before that, right? That is what the weaving does. So every time the 20 is there, everywhere, okay, so 25 and 10 will follow. They won't be before 20 at all. So that is a sort of a sequence what it follows. right? So that is the weaving, actually the weaving does. So now I'll just show you, the code is very easy that way, not so difficult. So this is our main function, all sequences, wherein we pass a tree node, okay, and this is a result which will actually gather all the sequence results. So it's a 2D array, correct? So now here, if you see my node is null, what I do is I pass an empty array, first actually store an empty array in my result, okay, and that is very important, because most of the base cases we have to do, right, something. And then what it does again, this is the all sequence here, okay. So this is my prefix which I start with, okay, and in the prefix I just push in the first node, okay, of my tree. And then these are the all sequences. I pass a node dash left, whatever I have come from here, the left subtree and the right subtree, okay. And then I, whatever I get, the result actually, whatever is the return, so it will be in the form of 2D array right here, okay. Then I just go through each and every array of the left subtree and right subtree, right, and then I weave it over here, okay. So my prefix is the one what we started here with the first node.
empty array.
Yeah, yeah, actually it pushes the node value first, whatever I get in the root node. So that is always my prefix starts with. And then if I pass this left and right subtree, and this will be my output. So whenever I get this output, okay, then I push into my results, okay. So this will be uh, another 2D array, right? So that is I'm going to push it at the end always, keep on pushing, because every time I get one, okay, then keep on pushing these, because I'll get more than one actually, because the viewing will be more, right? So if you look
Mhm.
at this weave list, whatever this function, that is the main whole implementation detail of this guy. Actually, see, so this is my first subarray, this is my second subarray, and this is my return results, and this is my prefix, the way it was described here. And if you look at the base case, it says that whenever the size of first is empty and second is empty, okay, then what I have to do is I have to take whatever I have in the prefix, okay, and that will always be the first one to go in the array, and then followed by whatever is remaining in my first and whatever is remaining in my second, just append it, okay. So it's just
Mhm.
happening one by one, and then you push back in my results. And this is the function where actually we do a two recursive calls for the same weave list. So this is one, and this is the second. But before doing that, what it does is, in this first case, in this is the first where we only recurse on the first array, and this is the second where we recurse on the second array, okay. So here what it does is pulls any element which is on the front of the first, okay, and then actually it removes that actually, therefore it is erasing, and then pushes back, it pushes back to the prefix, right? So pick up from the first of whatever is from the first array, and then push it back to the prefix, and then just call this recursive function, okay. And then at the end, when you come, you do backtracking again. So you just pop up whatever is there from your prefix, whatever you pushed over here, okay, and then you again insert it back at the same position, because you pulled it here from the front, right? So you
Mhm.
have to push it again in the front. So that is what is done. So the second one also is exactly the same implementation, but it's for the second array. So wherever there was first, we just change it to second, okay. So now we just pull any element from the second, the first from the front, and then again we erase it because we just want to remove it, and then we push it back to the prefix. Everything is same, but only we are using the second array. So first we do a recursion on this first array over here, we go to the end, okay. When we come here, the weaving array what I just showed you, right, which actually does for 1 2 3, first it actually removes one, that push it to the prefix, right, and then it goes, then it will again go in the recursive function. So it will pull second two also from the first array and push it to the prefix, right. And then when it comes here, at this time where your first will be empty, right, so you just actually append everything, and then when you come back you start uh, backtracking, correct. So when you
Mhm.
are backtracking, you actually remove two, and you insert that 2 in your first array, it's not complete, then you again start doing with the second one. So this is the way, because we actually move from one recursion of a first array to the second, there it actually starts weaving and it gives a different subsequences, right? So this is the very important part. Yeah, it will take some time to understand, but if you look at the implementation, it's very straightforward. But how to explain it, it becomes slightly critical. But if you look at the earlier function, what I was showing in this one node, it is exactly the same, right? So what it does is it removes the one from here, it puts in my prefix, right, for the first one, and then it removes, because it's still working on the first array, right? Removes this two,
Yeah.
and then it pushes to the prefix, correct? So
Yeah.
then when I've done that, so now my first is empty, and then I mix everything. Then I do start doing backtracking. So when I do backtracking, the last one which I've pushed in the prefix, I again push it into the front of my first array. But now, as you saw that, then it starts working on the second array, second array, right? So it removes the three, and then it pushes here, okay? So yeah, it is removed 3 and pushed here, but then it comes back to the first array again, because it's recursion, right? So it comes back and hits on the 2 and sees, okay, I still have a 2 in my first array, and then he pushes 2 here, right? Therefore you get and now first array is empty, so you get a 1 3 2 4, a different way, right? Earlier it was the 1 2 3 4, and then you got this 2 in between 3 and 4, correct? So
Yeah.
this was 3 4, and then it's when you use two recursions, for weaving the same function, then actually you are able to push this two. So if you look that way, the whole function implementation of whatever it is actually explained here, it does the same thing, and it very well, very neatly does all the weaving, though it's not an easy thing, but this is the main function here. Yeah, sorry, go ahead.
I'm saying it doesn't look intuitive, right? I mean, uh,
Yeah, yeah. So it is
like
not
what?
a straightforward solution. Absolutely, I agree. Yeah. But if you look the benefits of it, if you are just given because I also never thought like that, because if you are given a binary search tree, so how
Hmm.
many sequences you can form, or maybe if you take it the other way, right? If you are given any sequence, how many if you look at when any sequence, and if you are asked whether you can form a binary search tree, and the same binary search tree can be found with so many of different combinations, correct?
Yeah.
Right.
Yeah. So I thought that I'll fix one of the element and check how many trees are on. I mean, how many combinations are formed on left and how many on the right, and I'll multiply left into right. So corresponding to that one, but when I fixed that as a root, I got these many trees. Now again, I'll take second element, fix it as a root, and see how many trees on left and right, and multiply them. And corresponding to that, again I'll put, and so on so forth. I'll add all of them, and then return it as an answer. But it's totally different here, right?
Well, I think your thinking is correct. It's almost the same. It's not that different, you know. So what you are thinking is almost the same. If you look at, I'll just share the code again. So it is the same thing, right? You start with 50, okay?
Yeah,
Then you
yeah,
have a 20 as a one left subtree and 60. So what you are trying to do is you are trying to take 20 first, okay?
yeah. Mm.
And then now we don't have any more elements in your right subtree here, right? So therefore, whatever you have, you are actually using them first, right? So whatever is your 20 subtree, whatever you are having, but you can actually the same way you can multiply, right? So you can take this 20, okay, and then you can put it in any ways, okay, provided you are not actually messing the left and right subtrees sequence.
Yeah, that we have to take
Yeah,
care. Mm.
you just have to focus on whenever you put in any first you have put 50, right? That is the main root. Then you first, if you have put 20 as a left subtree, then you can put your right subtree anywhere, okay, no issues. But only what you have to be careful is whatever are the subtrees of the 20, they should always follow it. Same thing for 60 also. So whenever you place a 60, you have to place it in such a way that its subtree should follow it. So it's almost the same what you're thinking. But if you, so in your case, you first fix 50, as you said, okay,
Yeah.
then you fix 20, okay.
Hmm.
So now you know that you are free to anyway view all those whatever your subtrees of 20 they are, right? So you can view them anyway. So you can put 20, 10, 25 year, or you can have 10 year and then 25 year, okay. Because now we 60 we are having it here because we have to form many combinations, right?
Yeah. Hmm.
So that is
For
what you
60.
for, yeah, you first fix the root, then fix either a left subtree or a right subtree, and then you start actually playing with your other subtrees of the same roots, right? So it's
Yeah.
almost similar the way you are thinking, but it has so
Bec-
much of implementation details. Yeah, yeah. Sorry, go
No,
ahead.
I'm saying because we have a unique BST2 problem in lead code, which is the way the logic which I told. I
Okay,
don't know whether it is similar to this or not, but looks like somewhat it is similar to this, but still like this is like bit more. We have to focus on this to understand the approach which you are sharing. Like
okay.
first time I'm getting this that creating a prefix array and then
Right, right. I also saw that for the first time here. But if you are saying we can actually quickly look through what was the problem you said? Uh,
unique BST2.
Unique BST2, right? Okay.
Yeah,
Oh, sorry, yeah, it is right. I'm so sorry. Unique, huh.
no problem.
Yeah, unique BST2, right?
Yeah, yeah, BST2.
This guy? Uh, oh, there's no unique BST there. What
No,
did
no,
I do?
mm,
Did I spell it
it's
wrongly?
in DP. You can you click on DP?
Yeah, okay.
Can you click on DP? Here tags are there on there.
Okay. And then say unique.
And here if you go unique BST2 something like that. Yeah.
Okay, let me quickly search here. Unique.
Okay.
Oh,
Let
yeah,
me
this
search
one,
in
right?
my.
Unique BST, right? Two,
Yeah,
right?
yeah, yeah, yeah.
Okay.
Two. Yeah, this one. Yeah.
Yeah, so I didn't see that because I was trying to find out, but I
There also
put it
they're
in the
asking
answers.
like,
Okay.
is
Well,
this like no? Here they have given notes and asking us how many such
you're actually given
structural
an
BSTs
integer.
you can
Uh,
obtain.
so how many you can actually form? That is what it's saying, right? Generate all structural unique BSTs.
Yeah. So
So it is the sort of different
same
way, right? It's
same
a
thing you are also doing, right? Structurally, all the trees will be different, but possible BST, right?
no. In that case, we have a
Because
single
nodes are
BST.
same only. These are the
Well, yeah, if you look at that tree, you are given a
okay.
single binary search tree,
Yeah.
but you can have different inputs, different inputs to construct that binary tree. So you
You
can
have
have different
you
steps.
have different root.
Yeah,
See, this one the root can
Yeah,
change. The
little bit.
other one the root have to be
the
remain
same.
the same, and the order have to be maintained.
Yeah, then the order is important. Yeah, I think, yeah, we
Yeah.
have gone through this
Yeah.
once,
That
but
is
yeah, this is slightly different. But yeah, yeah, thanks for bringing this though. But at least we have some understanding about how things are. Yeah, but I really found this one very different, and it has not been seen anywhere. But this is very important. Whenever you have two recursive functions, one after another, you can imagine how much different things it can do. So if you handle them very well, you can have many combinations. So that was one very important thing about this mm, question. Okay.
problem. Yeah.
Yeah. So now let us move to the next one. Okay. So the next one. Okay. Let me share my OneNote again. Okay. So the next one is again from the same trees and graph. So this is about our random node. Okay. So what it says is you are given a binary search tree from, okay, binary search tree class from scratch. Oh, sorry, you are implementing, okay, binary search tree class from scratch, when in addition to insert, find and delete, which are the normal methods for a binary search tree in a class, it has a method, an extra one, which is get a random node, and this will return a random node from the tree. Okay, so all nodes should be equally likely to be chosen. So that is what the random probability and all those things are, right?
Yeah.
Yeah. So he says design and implement an algorithm for get random node and explain how you would implement the rest of the methods, right? So this one actually is a design type of question, correct?
Looks like yeah, design.
Yeah. So because when they are talking about where you are implementing a binary search tree from scratch, okay. So but they are not very clearly saying till this statement, right? In which insert, find, delete, they are methods, and has a get random method which returns a random node and all that, correct? So
Yeah.
when you come at this time, at the end it says like design and implement an algorithm, okay, but still it's not very clear. But uh, most of the time, uh, whenever it is like this, and when they are trying to give you some hints, implementing binary search tree class from scratch, so this means it's a design question. That is what actually the book says. And the reason why I'm bringing this up here is when you are in an interview, and sometimes someone gives you a hint like this, you should be able to catch it very quickly, that you have to
Okay.
actually, yeah, you have to have design a class, even though everything is very simple. But if you just fail to understand that, and then you start just implementing the get random node assuming that all these things are there, then you might miss the most important part of the implementation, right? So that is
Yeah.
what the book says. You be very careful because the wordings are very important, and that is what we need to focus on. Okay, so that is the main thing what she starts with in this book. Okay, so then in this book also, now as always, I always like the way CTCI explains, step by step, how most of the things are evolved to, and how it's broken down for the problem statement. So here also the same thing. Okay, so what they have done is they have taken many options. The first what they say is, okay, if you are given such a binary tree, right? Okay, so what you
Okay.
would do to start creating a get random node, right?
So
Yeah.
we'll generate a random number from 0 to length of the nodes. Any is it? I
Okay.
mean, we'll count total number of nodes in the binary search tree,
Mm-hmm.
and depending on that, any random number will generate from 0 to that length,
Right.
because all of them are equally likely to be chosen, right?
Correct. Uh-huh.
So uniformly they are distributed,
Yeah, I think you are on the right path. Yeah.
because most
Yeah.
of them in lead code, what we do like this only, like random dot choice 0 to whatever the length of
Correct.
that.
Correct.
Yeah, so it's same thing at Shashank. You know, we know the total, the count, right? The
Correct.
total number of nodes, and we randomly pick,
Uh-huh.
and then probably we just do the in order traversal one by one,
Mm-hmm.
and traverse to that node. You know, if suppose that node is number 3,
Uh-huh.
then we know that we pick 5, right? Because we do in order traversal,
Uh-huh.
and we return 5.
Okay. Okay. I think, yeah, you guys are good. Exactly. So that's what it says. So if you count all the nodes in this, and then and okay, she's doing it step by step, what you guys have
Yeah.
explained in a single step. So what she says, okay, first you do is you copy all the nodes in an array, right? Okay, but that's an O of n operation. That's still fine. Okay, and then uh, now as Leon said, right? You do in order, and that is what you do. You create an array of it. And Shashank, as you said, you just go count all of them, and then uh, say get random, and then find what is the node you want. So that
Yep.
node you can just pick it from that array and return it, right? So
Yeah, space will, yeah.
yeah, so that's very easy. So that is the first way we would think of, and that will involve O of n space and time. But there is one small issue in that, you know, because if you look at the problem statement, if someone is asking you in an interview, will that be so easy? Sometimes we need to think, right? Even
Yeah.
in some cases it might be, right? So if you carefully really understand this problem statement, what it says is, you know, you are supposed to uh, implement a class from scratch. Then you have to implement, maybe because you need, if you have not asked this question, do we have to implement these also, right?
Yeah.
So if you look at this, if you have just random number like this, right, and then it means that you are implementing this in one way, it's good also. But what will happen if you delete something, right? So will you again go in your this one and then look for, whenever you just implemented a get random node, right? And if you have not implemented insert, find and delete, you are depending on the your program to do that. Okay, if you are only focused on get random node, right? So if you delete, then how are you going to do? Are you going to go back again, count all the nodes and then form an array? That is possible, but in that case what's going to happen is you are always going to again do this O of n operations, right, every time. So will that be a really optimal way of doing it, right? So because usually we start every time a problem with the brute force, so we can think that way, right? In this case, even though it's not brute force, it's a very optimized one. But the case comes in when if you can ask always, if you are allowed to implement this, then we can always say, okay, when we am inserting, okay, I know that I have added one. So I first initially count all my nodes in my tree, and then when I insert, then I'll just increment one to my some size, because now I'm actually implementing the whole class, right, the random node tree class. And the same thing I can do for delete also. Okay.
So
But yeah, go
yeah, I
ahead.
was saying while deleting, let's say some node you have to delete from the array. So we did one problem where last element will pick and put it at that deleted place and then again sort it, because in order traversal of the BST will always be a sorted one, right?
Yeah, yeah.
But again, it's a more time consuming, right? Every time we'll have to sort it, login and login.
Yeah, you sort it, or maybe yeah, that is one way to do, right? When you are inserting, okay, as
Yeah.
you earlier said, you get all these in an array, okay.
Mhm.
So when you insert or delete, you can always even update the array, correct? So then you'll have to maintain it two locations. One you'll have to maintain a tree, and other will have to maintain an array also. So I think that might also be one option to do, okay. But again, you will have a extra space, right?
Yeah.
So can we still do it much better, can we avoid that? So that is what he's saying. So then in this case, what you guys were talking about, numbering all these binary tree nodes, that is what one thing what she says in the book also is almost the same thing. Like when you are actually labeling all the nodes, it's like you are labeling all the
Counting.
nodes, or yeah, in your array also the same.
Yeah.
Then or else what is say another option is saying, you can actually pick up a random depth. Okay, so you go from here and then you pick up random depth. Okay, like on, if you are on 1 2 depth, like you have 5 and 15, right? So you can say, you can again put on random and return either 5 or 15. Okay, so that is also one way of doing it. But in that case, whether are we actually satisfying the probability conditions, right? So that is one thing. It can work, but it might not be that efficient also, right?
Yeah.
So yeah, so in the other option, what she's saying is, like, you can actually say, I will divide my probabilities. One third will be on my current node, and one third will be on my left subtree and right subtree. So that is also a good way of doing it, right? So I will always select one third this part, one third the left subtree, and one third the right subtree. But it is also going to have the same problem like the random depth, because at the random depth, when you come in, you are actually not doing justice for all the levels, because in some levels you are having two, and in the third one you are having three, right? So the probability distribution in this case also, when you are saying my right subtree will be 3, one third, and left subtree will be one third. But if you look the nodes at left subtree and right subtree, they are not same. Correct.
Yeah.
So the last option it comes to, you can say you can count all the numbers in the tree because you are constructing the class, right? So you will always have the size of the tree. So you can say that I will select every node with a probability of 1 by n, right? So if you do that way, then actually things will be normal, right? So now you are saying that you are actually having a complete normal probability for, and then your probability distribution will also be very well distributed across all the nodes in the tree. Correct.
Yeah. So here, if you delete one node, then again probability will change. Like n will be 1 by n minus 1.
Right.
Like,
So for that you need to actually take care of all those stuff, right? So because when you delete, okay, so you already are implementing the delete function also. Okay, so you know how much elements you are having in the left subtree. So if you delete something in left subtree, then you can decrease that. If you are deleting right subtree, you can decrease that. Correct. Or if you insert it, then you increment in both subtrees. So you'll have to maintain a subtree wise size. Correct.
yeah.
So
So,
basically, yeah. Go ahead.
on the whole, the probability will change, right? If you delete one node, then I mean, now you are having 1 by n, like n nodes are there, but when you decrease, it got to n minus 1, right? So do we need to only change in the left, right, or like the entire probability will become 1 by n minus 1 for each of the nodes, right?
Correct. So yeah, it will change absolutely.
Yeah.
So what is the thing important thing here in this is like, whatever your class root node is, okay, so you usually have only left subtree, right subtree, and your value, right?
Yeah.
But here they introduced another attribute called size. So for each and every node, okay, you know what the size will be, right? The size will be actually the left subtree and right subtree plus the current node, right? So at
Mhm.
every node in a recursion, whenever you go, you know at that particular node how many nodes are below it in the left and right and counting itself. So now you know how much nodes you have. So then you can actually do that get random very well, right? So you can just take this random, okay, and then actually you just, if you say random of size, because you know the size of this based on your attribute, okay, and then you can just form an index. So if your index, whatever you get from the rand function, okay, if it is to the left, okay, because now you have a left size also, because if you go to the left node, okay, of your this function, right? So
Yeah.
you can actually get the size of that left subtree, and then you can see if your index falls in left subtree or right subtree. Okay, so this will be a right subtree. So you again go and recursively call. Okay, if it's in the left subtree, you just go and call the left subtree recursion. Okay, and if it is not, then you go to the right, or if it is, the index is on the same size of your current node, you return that node, right?
Yeah.
Yeah. So if you look at this insert node and all that, they have also implemented it almost the same. But at that time, you have to actually take care of your size everywhere. So that is very important, right? So it's the simple thing, right? When you are inserting it, you look at what the value is with your current node. Whether it is left, then you will put in the left subtree. If it is more, then you will put in the right subtree. If it is less than or equal to, you will put in the left subtree. Correct. And so this
Yeah.
is the same simple recursion, right? If your left subtree is null, then you have to create a new one, or you just keep on recursing. Same thing for your right. So this is the general binary search tree implementation for insertion, correct? And then you have an find also over here, right? So these are some of the very simple techniques, okay, for this one. And did you see any issues in this? Okay, so okay, let us actually go. Okay, this is the one implementation. This is the first approach, right? So
Yeah.
you have a random function. And here I've not shown the, I've not implemented the delete, but it will almost be the same. Okay, so if you run this, I'm just implement, because the book also didn't implement the delete, so I also didn't implement it. Okay, but the only problem with this, because they are using two approaches, right? So I'll just run the first approach, even if it is, so it's a simple thing, you know. Just look at this one. I'm looking for the random functions, and so you just ignore this part for now. As you see, when you are doing a random, you will get these randomized one, right? First time it is 15 year and 3 year, then I keep doing that. Okay, so 15 3, but they won't repeat all of them. uh, it is okay. Let me actually remove this, so things will be easier to follow.
Yeah, I thought like we do only we do random only once, and
Correct.
then we get the index.
Yeah, that's a very good observation. That's right. Yeah. So that was the point, you know. Actually, if we that is the only what you say downside of this implementation. Okay, because you are calling the random function in every recursive call, correct? So that is not good, right?
Yeah.
That is what that is the exact thing what Leon is trying to say. Correct, Leon?
Yeah,
Yeah. So because they say this random function is an expensive operation, correct?
Yeah.
So then we need to optimize on that. Okay, but I'll just show you the randomization. See, if you see 2017 was the second one, here it is 3, right? So it is randomizing very well. Okay, so I just wanted to show you that. Now see, you are getting 20, 30, 15, they are all different. Okay, if you have a huge number of nodes, then you will actually realize those things. Okay, so now what Leon said, that we are actually calling this random function always, and that is actually a very expensive function, expensive call, right? So if you see in the get random, you call this random, correct? When you go in this get random again on the left subtree, if you are actually your index is lesser than that, so again you come here and then again you call the random, right? So you keep on randomizing it, though it is good to randomize it more, but it's an expensive operation, right? So what the book says, can we avoid this? So we should only do random once, okay, and then whatever the value you get, you just return the node. That makes sense, right?
Yeah. One time.
Yeah, you just do a random one, and then you whatever you get your index, and you just go to the index and return the way you guys were talking. But this is not what is being done, even though it's good. But the second approach actually does that change, okay. And what it has done here, the same tree node remains almost the same, okay. But here actually there is one more function which is added. It's almost the same thing for as find, get the ith node, what it says. Whenever you pass any input, it will go and get the ith node based on these left and right subtree, you know, traversal, okay. And then you have the same insert order, it's nothing changed, size and everything. But only different thing what they have done is they have added another class called tree, okay. And this tree node has this tree has the root of the earlier class, okay. And then you it's initialized over here. Now this get random node is called from this tree, wherein you actually just run it only once, and then you take this root, and then you whatever your value you get, and you pass that input to this value, because then at your get ith node you are not calling it any random function anymore, right? So it's just actually abstracting another class, okay. So if you look at this function, they are not using any random function, and we are avoiding recursively calling the random function for each and every recursive call, right? This is a very simple limitation, but this is one thing what is shown. But you are using two different classes. because that makes sense, right? So you have to have a different function, or you could actually modify the tree node 3 class itself, and then add a wrapper to that and call that one. That also fine, but they actually have done it this way, so I just wanted to show it here. Okay.
Could you go back to the get random function, Santos?
Yeah, sure. Which one, this one or the previous one?
Uh, yeah, the calling function on line 157.
Or this one, right?
Yeah.
Okay. So this actually is the get ith node, and this is the function here.
Mhm.
So you actually take an input here, okay, and then you first find what is your left size, right? Because you have whatever your left node is. Based on that, you can go and correct the size. So that will be the size of your left subtree. So if your I is lesser than your left size, okay, then you go to the left ith node. And if it is equal, then you just return the current one, or else you go to the right. But when you are going to right, you actually are going to subtract I from the left size plus 1. You are going to subtract from I because you are going to the right, right? So that much amount you will be reducing
Plus 1 because
the root.
1 is the root.
Yeah, because of the root you have to subtract that, because the left will always show only the elements on the left subtree, correct? So it is not going to show you the current size, right? The size of your node. Therefore you have to add that one.
I see.
Yeah, yeah.
Yeah, because initially I was thinking that the right node, the right child will keep the size of like including the left child. I mean, the right subtree will have the size including the size of the left subtree, but this one that implement differently.
No, actually, see, for any subtree, okay. So if you look at the way size is implemented here, okay, it is added on incremented only when insert in order, and we don't have a delete function implemented. So this is the only place it is incrementing. But when you actually initialize the class, okay, so this will be the first size. It will be initialized to size 1, because that is what the root node will be, right? Correct. So this is
Right.
one. So when you add any left subtree and right subtree, any node to left and right subtree of this current node, okay, so then you will incrementing that size. So that means that, so all the nodes of the left subtree plus right subtree and this current node, okay, they will represent this variable value. You got the point, right?
Yeah.
So yeah, it is actually the complete size of the whole subtree from that particular current node, rooted from that current node. Yeah. So this is very actually, the way I always like about their implementation, whether it's a design question or any of these functions, right? The way it's implemented, everything modularized, and all these functions neatly written. Even the function names, they are really important in sometimes. So therefore, I usually tend to implement exactly the way they say, even though they have implemented Java. I keep everything, at least the names and everything same. I make some minor changes because in this case they are using tree node always, but I cannot use that because C++ has that implementation here, because that actually gives some problem. It doesn't compile, because I have already tree node and it doesn't like me again implementing another tree node, right? So therefore I just rename them. So minor changes I make, but try to maintain that and just add these stuff, to have a working solution. Okay. So this is one. And now I'll just quickly go to the last one, what I was talking about, thinking to do. I think we have done that many times. And this is about the paths with sum. So this says that this is the last problem what I would think here. And I think this is how we have done it many times in lead code also. So you are given a binary tree in which each node contains an integer value, okay, and it might be a positive number or a negative number. So you have to design an algorithm to count the number of paths that sum to a given value, right? And the path does not need to start or end at a root or a leaf, but it must go downwards, traveling only from parent nodes to the child node. Correct?
Yeah.
So how do we think of doing this one?
This is again like you're given. I mean, pre-order also you can do. You keep on adding from root to the leaf. I mean, wherever you find that you reach a required sum that is considered as one path, and then again initialize your sum to 0, right? Is it?
Mhm. Actually, yeah, you are given a sum, a target sum will be given,
Yeah.
and then your function signature will be, you will be given a tree node, a root of that, and a target sum. And then you need to find all, you need to return the number of paths actually which sum up to this target sum. Okay. So if we are given, suppose if we are given a target sum as 8, okay, and then we are given pointer to this root node at 10. Okay, so if you look at the paths of 8 will be like 5 and 3, right? So this 5 and 3, so this will be one path, correct?
Yeah.
And then I think this will be another path, because we are only allowed to go down, correct? So that is what says it must go downwards, traveling only from parent to child node. You don't have to say, like in this case, okay, if I just remove the what I've done just now, okay, sorry.
Then hash table we can use, right? 0 to -1, and then keep
Right,
on
right,
sub
yeah,
from the running sum, keep on subtracting the current node. Whenever you find that same sum is repeating, that means you can
right.
count it as one path.
Yeah, absolutely. That is one good thing. So if you look at this one, so you cannot actually include this path, right?
Right. Yeah.
So if you say, if you start from -2 plus 3 and 5 plus 2, even though it makes 8, but we are actually going from one node to another, that is not allowed. But we can go down, okay, from any node to its left or right subtree. Correct.
Yeah.
So that is what you can do. Okay. So so this was one path. This is the second path. And then do you see any other path in that other than this one? I don't think so, right? Yeah, 5 and 3.
Why don't we do the post order traversal?
Yeah.
So it
Post order.
always going through the root, from the root going down. I mean, go from a node going down.
Yeah. So you are saying your post order or pre order?
Post order.
Pre-order should work, right?
Uh,
Pre-order, like you say, maybe you need to keep track of extra pre-sum, right? Pre-sum, and then you, when you come back, I mean, when you see the value.
well, yeah, I think maybe I'm not sure about the post order, but the pre order should also be fine. And there might be ways to implement post order. Yeah, that's a interesting thing to look at.
Well, okay, so with the post order, let's see, think about there's a problem.
Mhm.
I think there's different problem, but there's a problem. Say, is there a path from the root down, to children with certain sum, but with, so let's say suppose right now the root at 5 and the target is 8, right?
Mhm.
So we just go down, from that route, we just go down the path and
Okay.
see, is there, any, as we travel down, we see any, uh, path that have to be begin at the root, and the sum to the target.
Mm-hmm.
Oh,
So you are saying
sounds
if you are at a post order, you have all the information and you can add them, right?
Yeah.
Okay. Yeah, I'm saying it's not. I'm not saying it's not possible, but the way it's implemented in the book, they use pre-order. But when you started talking about post-order, then I'm also thinking about it. So it didn't come to my mind. But it's good actually. You at least brought that. So yeah. So they are using a pre-order.
Okay.
Okay. Yeah. So they are actually using two approaches. The first approach is a brute force, and it says to go to each and every node, okay, and try all paths downwards, and from that node of the for the target sum. So what it says is you have to go start with every node, okay, and then when you come to a node, right? What is this? Okay, so you come to a node and then you try to find, if you are at this node, then you start finding all the paths which are of the target sum. Okay, am I lost? Yeah. So that is what it says.
Mm.
But then there is a downside. That is the reason it says brute force. So I'll just quickly show you the code. But before that, because because of time constraint, I would like to say that this one, if it is for a balanced subtree, the worst case will be n square in that case. But if it's a balanced subtree, it will be n log n. So it all depends on the balance tree. And the second optimized version, what Shashank was saying, was using a hash table, right? Right. So because this can actually be converted into our sub array problem, correct? So in a sub array, if you want to find any of those sums of the target sum, and if you are going through an array, if you have to do it in O of n operations, right? So we can use the help of hash table, right? So in this case, if we do that, then we can actually for in the worst case it will be O of n, but for a balanced tree it can be the height of the tree, log of n. So that is the way it can be reduced just by using a hash table. So I'll just quickly run through those implementations. Okay, and I think we have used those things, right, in our many of our lead code, and maybe even this one has been used. Okay, yeah, this is the LC437, which is also the similar implementation. Okay, so the first one actually what is discussed in the book is this approach. Okay, so we are given a tree node and we are given a target node. So we just return this is the base case, and then this is the function actually which does the counting of the paths. Okay, so counting paths with sum from node, that is what is called here. And if whatever we get, we actually push in this node here, and then the target sum, and this will be the initial value. And paths from root will return how many paths are of the target sum, that will return. And then we keep on moving in the recursive call to the left and right subtree, and how much numbers we get in, then at the end we add and return. So if you look at this counts path from some node, which is here, okay, so this is the way it does, because it comes to a node and now it has to go through all the paths, so again it has to do a recursion for on its left and right subtree. Okay, and then it keeps on adding your current sum. This is the value which initially it is initialized to 0 for every node. Okay, and then it keeps on adding its current node value. So whenever it is equal to a target sum, you actually increment your total path, right? And then your total path actually you go to your left and right, and what any number of total paths you get in, right? Then you return it from at the end of this one, right? Because then you have explored all the paths which have a target sum of 8 from this current node, right? Though it is a brute force, but it is also not a bad one, right? I
Yeah,
think you
right.
got it, right? Yeah, yeah.
yeah.
So the second one, what Shashank said about using a hash table, it's the most best way to do it, you know. So, okay. So it's slightly more implementation here. Actually, this is the function signature. You are given a root and then your target. Okay. Then this your map, another map. Okay. And then this is your one which starts your sum. So when we go in here, actually we look for the running sum, we keep on calculating it, right? And then we look for any paths, and then if they are in that are unordered map, okay, we keep on adding them over here. If it is not, then we actually increment, because sometimes it so happen that you will have many number of counts of the same value, right? So you have to increment that in your hash table, and then you go to the left subtree, right subtree, and then when you're done, you do backtracking by removing that particular number in your hash table. Okay, and then at the end you return total paths. So this is just an implementation of hash table where actually, so there is some small modularization done over here. Okay, so you can actually do everything, erasing and decrementing and incrementing at a single place. Okay, I think that's what was all. Maybe I can share the code if anyone wants later. Okay,
Yeah.
I think this is very simple. Okay, then I think I will stop this for now. We are only 4 minutes left, right?
Yeah.
Okay, so I'll stop the recording.